In this lecture, we look at an application of the Schrodinger equation in finding out the wave function of a particle in a one-dimensional potential box, or we also call it a one-dimensional infinite potential well. So imagine that the space is one-dimensional. We have only the x-axis and we have a particle. It may be an electron or a marble or a cricket ball, whatever you like, and that particle is free to move between x equal to 0 and x equal to L along this line. So in this region between x equal to 0 to x equal to L, in this region the potential on the particle is 0. There is no force acting on the particle and the particle is free to move. So it can be anywhere between x equal to 0 and x equal to L. At x equal to 0 and at x equal to L, there are two rigid walls. That is, the potential at these points at x equal to 0 and at x equal to L goes to infinity. So the particle which is inside this region, it does not have sufficient energy to penetrate this wall and go to the other side. So the particle can never exist between x equal to L and plus infinity. So in this region, the particle can never exist. Similarly, from minus infinity to 0, in this region also, the particle can never exist because the particle cannot break through this wall at x equal to 0 and go to this other side. So you see, the situation is like what we see in a well. Well means what we call kuo in Bengali. So if you have a particle placed in a well, you know that the sides of the well are bounded, so the particle cannot come out of those sides. So it is restricted to move only inside that well, and in our case, that well is one-dimensional, since we have assumed one-dimensional space. So this is the situation, and we wish to find out the wave function of this particle, which is restricted to move only between x equal to 0 and x equal to L. That is the purpose. So let us say that we want this wave function of the particle, which is given by capital psi xt. Now we have already discussed that if we assume this psi xt to be a function of psi which is only dependent on x and another function phi which is dependent on t. So if this is the product which gives you this capital psi xt, then we have discussed this already, that this phi t part of the solution will be e to the power minus I e t by h cut, where this e represents the energy of the particle. So this part of the solution is already known to us. We don't bother about that. So what we are interested in is to find this small psi x, and this small psi x will be obtained from the time independent Schrodinger equation. So in order to find out the wave function of this particle contained in this one-dimensional potential box, we essentially need to solve the time independent Schrodinger equation, keeping in mind that the time part of the solution is e to the power minus iet by h cut. These discussions we have already had in our previous lectures. You can refer to those videos. Now please note one point which is important, that according to our condition, the particle is allowed to move only between this x equal to 0 and x equal to L. So it can exist only within this region. Outside this region, that means from L to plus infinity, the particle can never exist. So the wave function of the particle in this region means from L to infinity, in this region it will have to be 0, because the particle can never exist, or there is no chance, no probability of finding the particle in this region. Similarly, from minus infinity to 0 also, in this region also, the wave function has to be 0, because there is no chance or no probability of finding the particle ever from x equal to minus infinity to x equal to 0. So whatever wave function that we are speaking of, this is true only for 0 to L. So this wave function will exist only between 0 to x equal to 0 to x equal to L. So this we should keep in mind. With that, let us solve this time independent Schrodinger equation to find out this small psi x. So please keep the picture in mind. I am erasing it off from the board. So as we said, we are solving for the wave function in the range 0 to L of x, and our time independent Schrodinger equation is minus h cut square by 2m d2 psi x by dx square plus v into psi x is equal to E into psi x. E was our separation constant, which represents the energy. So this is our time independent Schrodinger equation. In our case, when we are looking at this region x equal to 0 to x equal to L, the potential is 0. We have already said that the particle is free to move inside the box, so there is no potential acting on the particle. So let us put v is equal to 0 in our time independent equation, and we get minus h cut square by 2m d2 psi dx square is equal to E into psi x, since this v is equal to 0 in our case. Fine. So we can write this equation as d2 psi dx square equal to minus 2me by h cut square into psi x, or let us bring it to the left hand side and we get plus 2me by h cut square into psi x equal to 0. So this is our time independent Schrodinger equation, which we have obtained for this v is equal to 0 case. And as you can see that this equation is exactly similar to our equation of motion for a simple harmonic oscillator. If I put this 2me by h cut square as some k square, say, into psi x equal to 0. So look, this equation is exactly similar to d2x dt square plus omega square x equal to 0, which is our differential equation for a simple harmonic oscillator. So just as in this case, this xt comes out to be a sine omega t plus b cos omega t. So similarly, for this equation, if you solve by taking the trial solution and all, just by applying the same methodology as our SHM case, we can write this psi x as mind that here we have k in place of omega, so psi x will be some a sine kx plus b cos kx. So that is the general solution of this time independent Schrodinger equation for the particle in a one-dimensional box. So let me write it once again in one line. So psi x is a sine kx plus b cos kx. So this is your general solution. Note that here this a and b, these two are arbitrary constants which we need to determine. And how to determine those? We will determine those from what we call the boundary conditions. And remember, this k here which was there in this equation, this k square stands for 2me by h cut square. This is what we have replaced as k square. So what are our boundary conditions? We need those to determine this a and b. Look, we know in the first postulate, when we stated the mathematical conditions for this wave function psi x, we had said that a wave function has to be continuous at all points in space and time. So in our case, we have found this solution which exists between x equal to 0 and x equal to L. But at these boundaries, 0 and L, the wave function has to be continuous, because that is one of the important mathematical criteria of a wave function. So you see, in this region, our wave function is a sin kx plus b cos kx, as we have obtained. What about on this side, L to plus infinity? We have already said in this region the wave function has to be 0. Similarly, from minus infinity to 0, the wave function has to be 0, because the particle has no chance or no probability of existing in these two regions. Now, if my wave function has to be continuous across this boundary at x equal to 0 and x equal to L, what is the continuity of a function mean? The continuity of a function means that the left hand limit must be equal to the right hand limit, must be equal to the value of the function at that point. So if I want my function psi x to be continuous at x equal to 0, what is my left hand limit? On the left hand side, psi is 0. And on the right hand side, what is the function? This a sin kx plus b cos kx is my function. So if it has to be continuous at x equal to 0, then this function must reduce to 0. Only then the left hand limit and the right hand limit will match. So your first boundary condition is at x equal to 0, psi x must be equal to 0, because only then your function will be continuous across this boundary. The left hand side value and the right hand side value will be equal to the value at this boundary. Similarly, the second condition is, by the same logic, you see on this side psi is 0, it has to be 0 because particle cannot exist in this region. So the left hand limit, if this function approaches this x equal to L, this psi must drop to 0 so that it matches with the value on the right hand side of this boundary. So these are the two boundary conditions that we have. At x equal to 0, psi x must be 0. At x equal to L, also psi x must be 0. Let us apply them one by one. So from the first boundary conditions, if you apply here, so psi x is 0 and x is 0, so a sin 0 plus b cos 0. Now you see, sin 0 is in any case 0, so this goes, and cos 0 is 1. So from here I get p is equal to 0. So my first boundary condition gives me the value of this arbitrary constant b, which is 0. So if b is 0, then what is my wave function that is left over? So psi x is, therefore psi x is a sin kx. Fine. Now let us put the second boundary condition. So at x equal to L, psi x is 0. So x equal to L, this is 0, and that is equal to a sin k L. You see, I have put L in place of x. So I have a sin kl equal to 0. Now there are two conditions to satisfy this equation. A can be 0 or sin kl can be 0. Now look, if a is taken 0, then my wave function completely vanishes. There is no wave function left over at all. So that is not a situation that we are wanting. We are trying to find out the wave function of the particle. So if the wave function vanishes, that means there is no particle at all. So that is not the case. So A is equal to 0. This is not physical.
16 minutes.
Valid. It is not physically valid. So what I have? Sin KL is equal to 0. I repeat, why A is equal to 0 is not possible, because if you put A is equal to 0, the wave function vanishes completely. That means there would be no particle at all. But the particle exists in my box, so there has to be some wave function. So this is not a physically valid proposition. So we cannot take A is equal to 0. So this is not possible. So the only other way you can make this solution valid is sin KL equal to 0, which implies KL is equal to n pi, where n can have values 1, 2, 3, etc. So all integers starting from 1, n can have these values. N is equal to 0 is not possible, because again if you put n is equal to 0, then what happens? K turns out to be 0. Now K is related to the energy, so the energy would be 0, and again the particle would vanish. The wave function would vanish completely if you take n is equal to 0. So n is equal to 0 is also not a physically valid proposition, because in that case also the wave function will completely vanish, which we do not want. There has to be some wave function if there is a particle inside the box. So this n can take values starting from 1. All integer values are possible. So that gives you K is equal to n pi by L. Fine. So my wave function, therefore, I have got my psi x. That was my target, to find psi x. So K is n pi by L, and you have this x. So this is my psi x. And you see, we are not talking of only one wave function now. There are many wave functions, because n can take all integral values 1, 2, 3, etc. So basically, psi will be dependent on the choice of n. So you can have psi 1, psi 2, psi 3, different wave functions depending on the value of n. What does these wave functions correspond to? These wave functions correspond to the different energy values. Look, k square, this was my 2me by h cut square. Now k turns out to be n pi by L. So basically n square pi square by L square, this is your 2me by h cut square. So from this, what you get is a very interesting result, that E is equal to n square pi square h cut square by 2m L square. So you see, here n can take values 1, 2, 3, etc. That means the energy of the particle, E represents the energy of the particle. The energy of the particle is quantized. It can have only some specific values depending on the choice of n. So the particle moving inside that box between 0 to L, it cannot have any and every value of energy. A classical particle could have any value of energy starting from 0 to infinity. But here, when we apply the Schrodinger equation, we find that in this quantum mechanical case, the particle inside the box between 0 to L can only have some specific values of energy, or we say that the energy of the particle is quantized. What are the possible energy levels? As you can see here, if you put n equal to 1, then I get the lowest value of energy, which is pi square h cut square by 2ml square. M is the mass of the particle, by the way. If you put the next value of n, so E2, that is the next possible value of energy. So E2 is 4 pi square h car square by 2ml square, or in other words I can write it as 4 times of E1. The next possible value is for n equal to 3, which will be 9 times of E1. So as you can see, there can be no values between this E1 and 4E1, or between 4E1 and 9E1. So only some discrete levels of energy, E1, 4E1, 9E1, the next will be 16E1, then there will be 25E1. So only these discrete values of energy of the particle are allowed, and for each value of this energy corresponding to that, you will have a wave function. So when the energy is E1, my wave function would be psi1, so a sine pi x by l. When the energy is E2, my wave function would be psi2, which is a sine 2 pi x by l. So these are the space part of the wave function. The complete wave function, as you all know, that is the last thing which I will mention here today. The complete wave function, capital psi xt, is this psi x into phi t. So this capital psi xt would be a sine n pi by l into x e to the power minus I e n t by h cut. So where n is equal to 1, 2, 3, etc. So you see, you choose the appropriate value of n, and accordingly you get a wave function corresponding to a particular value of energy. So for these are the energy eigenvalues, we say these are the energy eigenvalues, E1, E2, E3, etc. And for each energy eigenvalue, you have a corresponding wave function of the particle. We are still left with the evaluation of this constant A, this arbitrary constant. This will come from the normalization condition. I will take this up in the next lecture. So we have understood in this lecture how to apply the Schrodinger equation to find the wave function and the energy eigenvalues of a particle restricted in a one-dimensional potential well.